Welcome to the Deep Dive, the show where we unlock the most impactful insights from cutting-edge research and documentation, translating them into actionable knowledge for you. Today, we're not just talking about chatbots that respond, we're diving into the transformative world of AI agents. These are intelligent systems that can truly reason, plan, and, act with incredible sophistication. Okay, let's unpack this incredible journey into building smarter AI. You've already done amazing work with chatbots, right? And you're proficient in prompt engineering, which is an absolutely fantastic foundation. Now we're going to equip you with the architectural blueprints to take that to the next level. Our mission today is to explore the foundational agentic design patterns. These are the core concepts that empower you to move beyond those static reactive systems to dynamic, proactive AI solutions. Imagine moving beyond an AI that simply answers questions to one that intelligently navigates complex situations, anticipates needs, orchestrates actions seamlessly, and provides truly tailored, compassionate support. That's the profound shift we're unlocking today.
It's about transforming your already impressive chatbot skills into the ability to build a truly proactive, intelligent assistant. We're going to unpack three core patterns that are, the essential building blocks for these sophisticated AI agents: prompt chaining, routing, and parallelization.
Indeed. And these patterns, they represent a fundamental shift. We're moving from static interactions and, single-turn responses to dynamic, truly intelligent systems. Think of it as learning the architectural language to design an AI that can adapt, reason, and make choices. And that's not just an upgrade. It's really a necessity for complex and sensitive applications like domestic violence crisis response. When you're dealing with delicate, high-stakes information, having an AI that can understand nuance, maintain context, and respond with precision is absolutely paramount. It's about building robustness and genuine intelligence where it matters most, ensuring that every interaction delivers the most effective support possible.
So let's kick things off with prompt chaining. You might also hear it called a pipeline pattern, and for good reason. What exactly is it? Well, imagine you're faced with a really big, complex problem, something that's just too much for a single monolithic prompt to handle effectively. Prompt chaining is essentially a divide-and-conquer strategy for large language models, or LLMs. Instead of trying to cram every instruction and constraint into one giant prompt, you skillfully break that daunting problem down into a sequence of smaller, much more manageable subproblems. Each of these subproblems then gets its own specifically designed prompt, perfectly optimized for its singular task.
Right. And the core idea here is elegant in its simplicity, but, profound in its impact. The output of one specific prompt is fed directly as input into the subsequent prompt in the chain. This establishes a clear dependency, a logical flow of information that guides the AI's thought process. It's almost like a meticulously designed factory assembly line, but for ideas.
Okay, so why is this so crucial, especially for the kind of critical support you're aiming to build?
Well, it introduces unparalleled modularity and clarity into your AI's thinking process. It makes it much easier to understand what's happening at each step. And crucially, it makes debugging significantly simpler if something goes wrong. You can isolate issues to individual links in the chain rather than trying to figure out what went wrong in one massive prompt.
Okay, that makes sense. So each step is optimized.
Exactly. Each step can be precisely optimized for a specific aspect of the larger problem, which leads to far more accurate, focused, and ultimately reliable outputs. This sequential information passing allows the LLM to refine its understanding, build upon validated results from the previous step, and progressively move towards a comprehensive, well-reasoned solution.
So what does this all mean for you, our listener, someone looking to build more robust AI for critical support scenarios? It means taking those big, overwhelming tasks that once seemed impossible for an AI to tackle and making them not just manageable, but solvable with incredible precision.
What's truly fascinating here is the analogy to human problem solving. As humans, we rarely solve genuinely complex issues in one instantaneous mental leap, right? We instinctively break them down into smaller sequential steps. We process information and build understanding piece by piece. Prompt chaining allows our AI systems to explicitly mimic that step-by-step reasoning. And that is absolutely vital for reliability when precision and accuracy matter most, such as analyzing sensitive information from a crisis situation. It ensures the AI's thinking isn't a black box, but a transparent, controllable sequence.
Right. That control is indispensable when lives might depend on it.
Absolutely. Indispensable when the AI needs to process and act on information correctly without fail.
That's an excellent point about mimicking human thought. But if prompt chaining is so powerful, what happens when we don't use it? What are the common pitfalls, the hidden traps, for someone trying to cram everything into one giant prompt?
That's a critical question, because when an LLM is overloaded with a single massive prompt trying to do too many things at once, well, several common failure modes inevitably emerge. These really compromise the reliability of the system. You might frequently observe instruction neglect. That's where the model simply overlooks parts of your prompt.
Just ignores it.
Yeah, pretty much, leading to incomplete or inaccurate responses. This happens because the, let's call it, cognitive load of handling too many simultaneous constraints just becomes overwhelming for the model. Then there's contextual drift. The model, as it tries to address too many different aspects simultaneously, sort of loses track of the initial context or the main purpose of the interaction.
So it might answer part of the question correctly, but miss the big picture.
Precisely. The outputs might be technically correct for a subpart, but irrelevant or even counterproductive to the overall goal. And a particularly insidious issue is error propagation. An early mistake or misinterpretation in one part of the response can amplify through the entire output, which can make the final result completely unusable or even harmful in a sensitive application like crisis response.
Yikes.
Yeah. Furthermore, trying to provide all necessary background info or instructions in one go often requires a longer context window, pushing the limits of what the model can effectively process and remember. This often leads to it getting insufficient information to respond accurately. And finally, with that increased cognitive load, the model's chances of hallucination significantly boost.
Meaning it just makes things up.
Confidently generates incorrect, fabricated, or misleading information, which is precisely what we absolutely must avoid in crisis response.
Right. Imagine trying to get an AI to simultaneously understand a nuanced crisis message, extract specific threats, assess the urgency, and then draft an empathetic, actionable response all in one prompt. A single prompt would almost certainly drop the ball on critical details. Like the source describes this scenario, analyzing a market research report. The single prompt asks the AI to summarize findings, identify trends with data points, and draft an email. While it might do one part okay, like the summary, it's very likely to fail on accurately extracting specific data or drafting a properly formatted email. It's just too much to juggle reliably.
That example perfectly illustrates the inherent challenge and really the need for a more structured approach. The solution then is precisely what prompt chaining offers: enhanced reliability through sequential decomposition. By breaking down complex tasks into these focused sequential workflows, you gain immense control over each step of the AI's process.
It certainly sounds like sequential decomposition is a powerful answer. But for our listener, thinking about implementing this in a critical support system, how does this granular control specifically translate into tangible benefits for, say, a crisis bot? Can you walk us through that market research example again, maybe with an eye towards what it teaches us for their specific needs?
Absolutely. Let's revisit that example, but think about the parallels to crisis response. First, you'd have an initial prompt for summarization, something like, summarize the key findings of the following market research report, .text. The model's sole focus is summarization. Now, for a crisis bot, this could be summarize the core details of the survivor's initial chat message, focusing on their immediate needs and expressed feelings. Chat transcript. See, the AI's job is just to grasp the essence, not solve everything yet.
Okay, just get the gist first.
Exactly. Second, a trend identification prompt. Using the summary, identify the top 3 emerging trends and extract the specific data points that support each trend. Output from step 1. Notice how this prompt now builds directly upon the validated, concise output of the first step. It's not starting from scratch. For our crisis bot, this translates to something like, based on the summarized needs, identify any immediate safety concerns, specific types of assistance requested, like shelter, legal advice, and urgent keywords like danger, help now. Summary from step 1. The AI is now extracting critical, structured information.
Right, focused extraction based on the initial summary.
Precisely. And finally, a third prompt for email composition. Draft a concise email to the marketing team outlining the following trends and their supporting data. Output from step 2. For the crisis bot, this will become, draft an empathetic, action-oriented initial response to the survivor, incorporating the identified needs and suggesting relevant, immediate resources, extracted safety concerns and assistance needs from step 2.
Ah, I see. So the decomposition gives you much more granular control. Each step is simpler, less ambiguous.
Which significantly reduces the cognitive load on the model. And that leads to a more accurate and reliable final output. It's like a computational pipeline where each function does one specific, specialized job extremely well. And here's where it gets really interesting for your crisis response chatbots. Instead of that single solve everything prompt, you can have your AI first identify the core need from a survivor's message. Second, extract critical safety information like location or immediate threats. And third, suggest immediate tailored resources or actions. Each step is focused, therefore more reliable. You can even assign distinct roles to the model at each stage.
Roles, like what?
Like crisis analyst for the first step, safety information extractor for the second, and maybe empathetic communicator for the third. This helps ensure the tone and focus are precisely what's needed for such sensitive interactions.
That deep level of precision is absolutely critical when dealing with sensitive, urgent situations. Misinterpretations could have serious consequences. But how do we ensure the output of one role, one step, is perfectly understood and usable by the next, especially when precision is paramount? This brings us directly to the critical role of structured output, right? Because the reliability of any chain depends on the integrity of the data passed between steps.
Exactly. If the output of one prompt is ambiguous or poorly formatted, the next prompt gets faulty input and might fail. That causes the entire chain to break down. So it raises that important question. How do you ensure the information flowing through your chain is not only accurate, but also consistently formatted for downstream consumption? Structured output, typically in machine-readable formats like JSON or XML, is the answer.
Like the example from the source. With the market trends.
Precisely. The source shows trend identification output formatted neatly in JSON, trends, trend name, AI-powered personalizations, supporting data, trend name, sustainable and ethical brands, supporting data. This structured format ensures the data is machine-readable and precisely parsed. It minimizes errors from the ambiguities inherent in natural language. For a crisis bot, this could mean ensuring extracted details like caller's location, type of assistance needed, identified threats, or preferred contact method are always in a predictable, machine-readable format. This makes them immediately ready for the next step, whether that's dispatching an alert, searching a database for specific local resources, or updating a case management system. It's key for building robust multi-step systems you can trust in high-stakes environments.
That level of reliability and consistency is truly a game changer for critical applications. Okay, so with this power of sequential structured reasoning, what are some of the practical applications? Where does prompt chaining really shine, especially for supporting domestic violence crisis response organizations?
Prompt chaining is incredibly versatile. It fundamentally enables agents to tackle more complex, meaningful tasks. For information processing workflows, it allows agents to handle multi-stage tasks like summarizing documents, extracting key entities, querying databases, generating reports, all in a controlled, auditable sequence. So for a crisis context, imagine your bot receives a lengthy free text report from a survivor. The chain could first extract the full text, then summarize key events, then extract specific names, locations, incident types, and finally use those structured details to intelligently search an internal knowledge base of local shelters, legal aid, support groups, all without losing context or accuracy along the way.
That's powerful. What about answering complex questions?
Yes, for complex query answering, it enables sophisticated multi-step reasoning. Instead of trying to answer a multifaceted question like, what are the immediate legal steps for a survivor in city name, and what local resources offer free consultation for a restraining order in one go? Well, you break it down. Prompt 1 could identify the sub-questions, legal steps, local resources. Prompt 2 could research relevant legal steps for that specific city. Prompt 3 could then search for local resources offering free consultations. And Prompt 4 could synthesize all this information into a comprehensive, accurate, actionable answer, ensuring no detail is missed.
Right, breaking down the query itself.
Exactly. Data extraction and transformation also benefits immensely. Converting unstructured chat transcripts or intake forms into structured, database-ready data is often tricky. You can design a chain where prompt 1 tries to extract critical fields: incident type, urgency level, number of dependents, contact preference. Then maybe some processing logic checks if all fields are valid. If not, a conditional prompt 2 might specifically ask the model to re-examine the text and find the missing information. This is essential for normalizing data for a database. You could even delegate calculations, like elapsed time since an incident, to an external tool if needed, integrating the LLM with other resources.
And for your work in crisis response, this can extend powerfully to content generation workflows. You're not just asking for any response. You're building a multi-stage process for empathetic, clear, safe communication. This could involve an initial prompt to outline the key sections of a safety plan based on the extracted info. A second prompt drafts the emergency contact section. A third drafts immediate safety steps. A fourth drafts legal protections specific to their location. Each output is then refined, maybe by subsequent prompts, ensuring the final message or safety plan is accurate, appropriately toned, comprehensive, and truly supportive.
It's also foundational for developing conversational agents with state. Now, comprehensive state management involves more than just chaining, but prompt chaining provides the mechanism for preserving that conversational continuity. Each turn of the dialogue can be constructed as a new prompt that systematically incorporates information or extracted entities from the preceding interactions. This ensures a crisis bot remembers previous utterances, identified intents, key entities across the conversation, providing coherent, continuous support. It updates a conversation state as it goes, so the bot feels far more intelligent and helpful than a stateless system that forgets everything each turn.
Which is vital for building trust in a crisis situation.
Absolutely. And for our listeners' technical skills, code generation and refinement is another strong use case. Decomposing typing tasks means your AI can first generate pseudocode, then an initial Python script draft, then identify errors or suggest improvements, maybe rewrite or refine the code, even add documentation or generate test cases. This transforms the AI into a powerful coding assistant. Think about generating Python scripts for data analysis on crisis trends, helping you analyze patterns in survivor requests or resource utilization.
And finally, a cutting-edge application. Maybe not for every crisis scenario today, but with immense future potential. Multimodal and multi-step reasoning. The idea of interpreting complex data sets, say, an image with embedded text or data fits chaining perfectly. It requires breaking down the problem. Extract text, link to visual labels, interpret the combined info, or imagine a survivor sends a voice message. Processing could happen in parallel. Transcribe words, analyze tone for distress, identify background sounds, suggesting danger before a single text response is even generated.
That allows the AI to perceive layers of information a human might miss or take longer to process, leading to a much more informed and rapid intervention strategy, potentially even in scenarios involving image-based evidence or documentation in the future.
Okay, let's look at a hands-on code example using LangChain. This demonstrates a two-step data processing pipeline. Parse unstructured text, extract specific info, transform into structured JSON. It's a great example of how prompt chaining works in practice, giving you a clear mental model.
And this code example is incredibly practical. It's immediately adaptable for crisis response. Consider this as a blueprint. Step 1, extract core details from a survivor's initial message. Are they safe? Immediate help needed. Specific abuse types mentioned. Step 2, transform those extracted details into a structured JSON object. This JSON can then be seamlessly passed to a database or another agent to trigger the right action, logging the incident, initiating a safety plan, alerting a human caseworker. The full chain in the code elegantly shows how the output of the extraction chain becomes the input for the prompt transform. It makes that dependency clear and your code modular.
Precisely. Let's walk through it. First, install the libraries. Pip, install LangChain Community, LangChain OpenAI LangGraph. Then you set up your LEM, maybe Chat OpenAI, temperature 0 for factual responses, or Chat Google Generative AI model Gemini 1.5 flash temperature 0 if you're using Google's models. Next, define your two prompts. Prompt extract takes text input and asks the element to extract the technical specifications. Then prompt transform takes specifications, which will be the output from step 1, and asks to transform the following specifications into a JSON object with tape-view, memory, and storage as keys. This clearly specifies the desired structured output.
Right, being explicit about the structure is key.
Exactly. The magic happens with the chain building using LangChain Expression Language, or LCEL. Think of it like piping commands in a shell script, but for AI sequences. It's super intuitive. You create extraction chain equal prompt extract, LEM's strutput parser. This MIDI chain takes raw input, applies the prompt, sends it to the LLM, parses the output to a string. Simple. Then, for the full chain extraction chain prompt transform strut parser, the specifications extraction chain part is crucial. It means the output of our extraction chain is fed directly into the specifications variable as input for prompt transform. It's a clean, readable way to define that data flow, much better than complex manual Python function chaining, which can get messy and error-prone.
LCL makes it very declarative.
Totally. Finally, you execute it with some input text, like the new laptop model features a 3.5 GHz octa-core processor, 60 GB of RAM, and a 1 TB NVMe SSD. And when you call final result fullchain.invoke, it runs through both steps, giving you that structured JSON output ready for further processing or storage.
It's a very clear illustration. decompose the task, manage the information flow precisely. By now, you're not just thinking about crafting individual prompts, you're orchestrating entire sequences of AI thought. And this shift in perspective naturally leads us to a broader, more powerful concept underpinning effective agentic design: context engineering.
This sounds like a big leap. You're already a pro at prompt engineering, which is definitely part of the picture. But now we're talking about building an entire operational world around our AI. Would you say this context engineering is like giving our chatbot peripheral vision and memory, truly moving it beyond just a reactive question-answer system?
That's a perfect analogy. Prompt engineering, as you know, focuses on optimizing the phrasing of the immediate query, making that single instruction as effective as possible. Context engineering, however, is a systematic discipline. It's about designing, constructing, and delivering a complete informational environment to an AI before it even starts generating its response. If you look at the diagram in the source, you'll see prompt engineering is just one piece, strategically nested within the broader discipline of context engineering. It's about providing the AI with the full picture, not just a snapshot.
Okay, so what are these layers of information that make up this comprehensive informational environment in context engineering?
They're quite diverse, ranging from foundational to dynamic. At the core, you have the system prompt. This provides foundational, often fixed instructions like, you are an empathetic crisis support agent. Your tone must always be compassionate, clear, action-oriented, prioritizing survivor safety. It sets the AI's persona, ethical guidelines, operational parameters. Then you have crucial external data. This includes two main types. First, retrieve documents, where the AI actively fetches relevant information from a separate knowledge base. Think RI, retrieval augmented generation. The AI gets facts before generating, grounding its response. Second, tool outputs. These are results from the AI using an external API like querying a database for local shelters or checking legal aid availability.
Got it. System prompt, retrieve docs, tool outputs. What else?
Finally, there's vital implicit data. Things like the user's identity, if known and consented, the interaction history within the current conversation, and the overall environmental state of the system or application. The core principle here is profound. Even the most advanced LLMs will underperform if given a limited or poorly constructed view of their environment. Model quality depends far less on its architecture and far more on the richness, relevance, and structure of the context provided. This reframes the task. It's not just answering a question, it's building a comprehensive, living operational picture for the agent, allowing it to act with true awareness.
That's incredibly powerful. Connecting this back to crisis response, a context-engineered bot wouldn't just respond to the immediate words. It could potentially understand the user's history with the service, previous interactions, relevant local laws about domestic violence in their specific area, available local resources, all integrated seamlessly to provide a truly informed, personalized, empathetic response. That's a huge advancement for survivor support, moving beyond generic help to truly tailored intervention.
It fundamentally transforms stateless chatbots, those operating turn by turn without memory, into situationally aware systems. Systems that can maintain deep context across extended interactions. Implementing this involves designing robust pipelines for fetching and transforming data at runtime, maybe even setting up feedback loops for continuous improvement. Advanced tools like Google's Vertex AI Prompt Optimizer can systematically evaluate and refine these contextual inputs, enhancing model performance over time without constant manual rewriting. This ensures your crisis bot continually improves its ability to provide life-saving support.
Okay, let's quickly summarize prompt chaining then. What? Complex tasks often overwhelm LLMs in single prompts. This leads to increased cognitive load, errors like instruction neglect, context loss, and crucially, hallucination making stuff up, which is dangerous in a crisis. Why? It masterfully breaks complex problems into smaller, interconnected subtasks. Focused prompts dramatically improve reliability and control. The validated output from one step becomes the precise input for the next. It allows crucial external tool integration and ensures structured data passing, boosting information integrity. Rule of thumb: use it strategically when a task is too complex for one prompt, involves multiple distinct processing stages, needs external tool interaction, or when building any multi-step agentic system where reliability and precision are paramount.
And looking at the visual summary, figure 2, you can clearly visualize that elegant flow. User prompt agent, 1 output input, and 2 output input, and so on. A controlled, logical sequence, culminating in a final output to the user. This structured flow is key to building complex yet reliable AI behaviors.
So the key takeaways for prompt chaining are clear. It breaks down complex tasks into smaller, focused steps, the pipeline pattern. Each step involves an LLM call or other logic, using previous output as validated input, building progressive understanding. Improves reliability, manageability, and auditability of complex LLM interactions. Debugging gets easier. And powerful frameworks like LangChain LangGraph, Google ADK provide robust tools to define, manage, and execute these sequences, handling much of the complexity. It's all about building robustness, control, and sequential intelligence into your AI. Okay, so with prompt chaining, we built a solid, reliable highway from A to B to C, ensuring each step is precise. But life, especially in crisis, isn't always a straight shot, is it? Sometimes you need to turn right, sometimes left, sometimes pivot entirely based on urgent new info. That's where routing comes in. It's like your AI's internal GPS, making it truly smart and responsive by dynamically choosing the best path forward.
Exactly. While chaining is foundational for linear workflows, real-world agents need to be adaptive, not just sequential. Routing introduces that conditional logic. It allows agents to choose dynamically between multiple potential actions or pathways based on factors like environmental state, nuanced user input, or previous outcomes in the conversation.
So it's the decision maker.
Precisely. This is where we truly elevate the intelligence. Instead of rigidly following a predefined script, a routed agent can interpret the specific situation and intelligently choose the optimal path from a multitude of options. Routing effectively governs the flow of the entire system. It directs control to specialized functions, specific tools, or even entirely different sub-processes or sub-agents that are best equipped for the current need. This shifts us from fixed, predictable execution paths to dynamic, context-aware evaluation, leading to much more flexible and genuinely adaptive system behavior.
And for a domestic violence crisis, Bob.
For that context, this could mean discerning, with high accuracy, if the user needs immediate emergency contact, detailed legal aid info, specific shelter availability, or just a safe space to talk and process emotions, and then directing them to the precise, most appropriate support pathway instantly.
Okay, how does this dynamic decision-making actually work? The source gives a great example of a customer inquiry agent. It really illustrates this well. First, it analyzes the user's query, understands the core intent, then it uses that understanding to route the request. If the intent is check order status, it routes to an order database tool. If it's product information, it intelligently goes to a product catalog tool. For technical support, it routes to troubleshooting guides, or crucially, to a human escalation pathway. And if the intent is unclear, it routes to a clarification subagent to ask follow-up questions. That's the essence of adaptive behavior, moving from one linear flow to a responsive multi-path system.
That example highlights the power of intent-driven redirection. The core component of the routing pattern is precisely the mechanism that performs this intelligent evaluation and directs the flow. And there are several powerful ways to implement this, each suited for different scenarios. LLM-based routing is where the language model itself, often with a carefully crafted prompt, analyzes the input and outputs a specific identifier for the next step. For example, it might be prompted to output only order status, product info, or technical support. The system then directs the workflow based on that unambiguous classification. This is highly flexible for natural language.
So the element itself decides where to go next.
In a sense, yes. Then there's embedding-based routing. Here, the input query is converted into a vector embedding a numerical representation of its semantic meaning. This embedding is then compared to embeddings of different predefined routes or capabilities. The query gets routed to the most semantically similar route. Excellent for decisions based on the meaning and nuance, not just keywords.
Interesting. And you also have rule-based routing, right? The more traditional way.
That's right. This uses predefined explicit rules like if-else statements or switch cases based on keywords, specific patterns, or structured data. It can be faster and more deterministic for clear-cut cases, but it's inherently less flexible. It struggles with the nuances of natural language inputs, often used for initial, rapid triage, or simple classifications.
Makes sense. And the last one.
Finally, there is machine learning model-based routing. This employs a discriminative model, typically a classifier, specifically trained on labeled data for routing tasks. It's distinct from LLM-based routing because the decision logic is encoded in the fine-tuned model's learned weights, not through generative inference. LLMs might help generate training data, but they aren't making the real-time decision. These routing mechanisms can be applied at multiple points, at the start to classify the main task, at intermediate points to decide the next action, or even within subroutines to pick the bugger tool.
And frameworks help manage this.
Yes. Frameworks like LangChain, LangGraph, with its state-based graph approach for complex scenarios, and Google ADK, the Agent Development Kit, Google's specialized toolkit for sophisticated multi-agent systems, provide explicit constructs for managing this conditional logic. Looking at figure 1 in the source again, you can visualize the user prompt going into an intelligent router, often LLM-based, which then dynamically directs the flow to one of several specialized agents or tailored outputs. It embodies true adaptive intelligence.
So what does this mean for you, the listener? Routing transforms your AI from a predictable script follower into a truly dynamic system that can make intelligent decisions. It's about building an AI that can triage, classify, adapt its behavior to an evolving situation, which is exactly what you need in the unpredictable, high-stakes environment of crisis response. Let's look at some powerful practical applications and use cases.
In human-computer interaction, virtual assistants, tutors, or, crucially, crisis bots routing is fundamental. It interprets diverse user intent and responds appropriately. For a domestic violence crisis context, this means routing initial natural language queries from survivors to determine their precise intent. "I need to leave now" could trigger an immediate emergency response pathway, maybe activating location services or contacting emergency services. "What are my legal rights?" Routes directly to legal aid info and pro bono lawyer databases. "I just need someone to listen." Could direct them to an emotional support pathway, connecting to a specialized empathetic subagent or a human counselor. This allows contextually sensitive, precise support.
Moving beyond linear dialogue flows is key there.
Absolutely. For automated data and document processing pipelines, routing acts as a classification and distribution function. It streamlines complex workflows. Imagine routing incoming support tickets or emails based on urgency, keywords, sender details to the right automated workflow. An urgent safety plan request goes one way, triggering a detailed safety planning agent. An information request about local resources goes another. A follow-up message might go to a case management agent. Ensures prompt, accurate handling.
Okay. And for systems with lots of agents?
Yes, in complex systems with multiple tools or agents, routing acts as a high-level dispatcher or orchestrator. A central crisis response agent could receive a broad request and then intelligently route it to a shelter finder agent, a legal resource agent, a counseling agent, or a child support agent based on the survivor's stated need. This ensures every interaction gets the most appropriate, effective, specialized response, coordinating a whole network of AI capabilities.
Now, let's dive into a hands-on code example for routing using LangChain. This shows an agent-like system where a coordinator intelligently routes user requests to simulated sub-agent handlers based on intent, like a dispatcher for emergency calls.
This example beautifully demonstrates the brain of a routing system in action. You can clearly see how a crisis message could be classified by intent, immediate danger, seeking resources, emotional support, info request, and then seamlessly routed to a specialized subagent or tool designed and optimized for that specific need. This ensures every interaction is met with the most appropriate, effective, and crucially rapid response, which is paramount in crisis situations.
First, the installs, pip install, LangChain, LangGraph, Google Cloud, a platform, LangChain, Google, GNI, Google Ad, deprecated Pydantic. Then initialize your LLM, maybe OLM, Chat Google Generative AI, model Gemini 1.5 Flash, temperature 0, for a capable Google model with low creativity. Next, define simulated sub-agent handlers. Booking handler, info handler, unclear handler. These are just simple Python functions simulating what a real specialist agent would do. For example, booking handler might return simulated booking action taken for temporary accommodation. In a real crisis bot, this might call an API checking shelter availability or initiate secure comms with a human booking specialist.
Right, they're placeholders for the real action.
Exactly. The crucial part is the coordinator router prompt. This is a chat prompt template meticulously instructing the LLM. Analyze the user's request. Determine which handler. Only output one word. Booker, info, or unclear. That strict output constraint is vital for reliable routing. Then coordinator router chain, coordinator router prompt kiln strap parser. This chain takes the request, asks the LLM to classify intent, and gives us that single unambiguous word decision.
Then comes the delegation logic using LangChain's runnable branch. You define a dictionary of branches mapping the LLM's classification booker, info, unclear to specific actions, usually assigning the output of the respective handler. The delegation branch is then created using runnable branch with conditions like lambda x decision.strip equals is booker, branch is booker. This literally means if the decision from the LLM is booker, then execute the booking handler, passing along the original request. It's a powerful way to define conditional logic programmatically.
Exactly. And the coordinator agent combines it all. Coordinator agent, real chain, request, runnable path-through, delegation branch, lambda XX output. This takes the original request, gets a classification decision from the router chain, uses that decision to route the original request to the correct handler, and finally extracts the output. When you invoke it with requests like, book me a flight, what's the capital of Italy, or tell me about quantum physics, you see it intelligently routes to the correct simulated handler. The beauty is using the LLM's natural language understanding for the decision and structured code for the action.
Moving on, Google's ADK, the Agent Development Kit, offers an alternative, more framework-driven approach. It emphasizes defining clear agent roles and tools. Here, routing is primarily implemented by defining a discrete set of tools representing agent functions, along with clear instructions. The framework's internal logic then uses an underlying model to match user intent to the correct handler or subagent. This is often called autoflow.
This ADK example offers a different flavor, maybe more appealing for larger systems. The coordinator's instructions are paramount here, guiding the internal autoflow to pick the right specialist agent. For you, our listener, this means you can define clear roles: safety plan agent, resource locator agent, legal aid agent, then trust the framework to direct queries appropriately. It streamlines development of complex crisis systems without coding every if-else condition explicitly. It's a powerful abstraction.
In the ADK code, you first define simple Python functions like booking handler, info handler, simulating specialist actions. These are then explicitly wrapped in function tool objects, making them discoverable by ADK. Next, create specialized subagents, like booking agent and info agent, each explicitly described with its purpose and equipped with its relevant tool, like the booking agent described as, handles all travel and accommodation booking requests.
So the descriptions are key for the routing.
Yes, very important. The key component is the parent coordinator agent, defined with a name, a model, for example, Gemini 2.0// and critically, an explicit instruction. This instruction clearly outlines the routing logic. Your only task is to analyze incoming user requests and delegate them to the appropriate specialist agent. Do not try to answer the user directly. It then specifies rules like, for any requests related to booking flights or hotels, delegate to the booker agent. The subagent's booking agent, info agent parameter is what enables ADK's LLM-driven delegation, or autoflow. The coordinator itself uses its LLM to decide which subagent is best based on the user input and those subagent descriptions.
Got it. So instead of explicitly coding the runnable branch, like in LangChain, the ADK framework handles that intelligent routing internally, driven by the coordinator's clear instructions and the subagent definitions. When you run coordinator.run with requests like, book me a hotel in Paris, or what's the highest mountain, the coordinator automatically routes them to the correct specialized agent, and you get the final result. It lets you focus on what agents do, not how they decide where to go.
Okay, routing at a glance. What? Real-world agentic systems need to handle diverse inputs that a single linear process can't manage. Sequential workflow lacks adaptive decision-making. Why? It introduces crucial conditional logic, analyzes incoming queries for intent nature, then dynamically directs flow to the right tool function subagent. Allows various decision methods: LLMs, rules, embeddings, rule of thumb. Use routing whenever an agent must decide between multiple distinct workflows, tools, or subagents based on dynamic factors like user input, conversation state, or external data. Perfect for a crisis support bot triaging diverse requests.
So the key takeaways for routing are profound. Empowers agents to make dynamic, intelligent decisions based on conditions. Allows truly adaptive behavior beyond rigid linear execution. Routing logic can be flexible, LM-based, rule-based, or embedding similarity for semantic understanding. And frameworks like LangGraph and Google ADK provide structured, robust ways to manage this complexity, offering different architectural approaches. This pattern is all about intelligent arbitration, adaptability, and getting the right help to the right place fast. Okay, we've learned how to break down complex tasks into manageable steps with prompt chaining, and how to make smart, adaptive decisions about which path to take with routing. But what if you have, say, 3 different things that don't depend on each other, and you want them all to happen at the same time? That's where we make your AI super efficient, super fast, highly responsive with parallelization. This is crucial for real-time support, wouldn't you say?
Absolutely. Efficiency is paramount, especially in crisis situations where every second can be critical. If your AI can gather 3 pieces of vital information simultaneously rather than one after the other, well, that's not just a convenience. It's a direct, tangible improvement in responsiveness and potentially life-saving speed. This pattern helps us build systems that are not just intelligent and adaptive, but also incredibly fast, scalable, and capable of meeting urgent demands. Parallelization involves concurrently executing multiple components, LLM calls, tool usages, data fetches, even entire subagents at the same time. The core benefit: a significant reduction in overall execution time by running independent tasks simultaneously.
Instead of waiting for each one to finish. The source gives a great example with a research task. A sequential approach would be, Search source A, summarize A, search B, summarize B, synthesize A plus B. That takes time. Each step waits. But with parallelization, search A and search B simultaneously. Cut down gathering time. Then summarize A and summarize B simultaneously. Only then the sequential step, synthesize A plus B. The trick is identifying workflow parts that don't depend on each other's immediate outputs. If they don't need results from others to start, run them together.
Right. And this is particularly effective with external services like APIs or databases, which often involve network latency. You can issue multiple requests concurrently, making the most of that waiting time. If you look at figure plot 1 in the source for parallelization, you can visualize a single input going into a parallel agent. This then branches off to multiple sub-agents, agent 1, 2, 3, each producing its own output concurrently, a powerful visual of simultaneous action.
And frameworks support this.
Yes, modern agentic frameworks like LangChain, LangGraph, Google ADK are specifically designed to support asynchronous execution. Makes it easier to define and manage these parallel steps. This built-in capability is vital for improving responsiveness, especially when dealing with multiple independent lookups, computations, or even distinct generative tasks. It's about doing more in less time.
Let's explore some powerful practical applications, keeping our critical crisis response context firmly in mind.
Okay. For information gathering and research, this is a classic and immediately impactful use. An agent responding to an urgent request from a survivor could simultaneously: 1. Check a database for local law enforcement contacts specific to their jurisdiction. 2. Search for nearby shelter availability meeting specific criteria: child-friendly, pet-friendly. 3. Retrieve relevant legal aid hotlines and pro bono services in their area. All these info-gathering tasks run concurrently. Provides a comprehensive, rapid response, delivering crucial support much faster than sequentially.
Huge time saver. What about data analysis?
In data processing and analysis, you could analyze a batch of incoming crisis reports or chat transcripts, concurrently run sentiment analysis for urgency, extract keywords for resource matching, and categorize the incident type: physical, emotional, financial abuse. This gives a multifaceted analysis quickly, enabling faster triage and more informed decision-making for human operators.
Makes sense. Interacting with multiple tools.
For multi-API or tool interaction, if a survivor needs to reach a safe location, your AI could concurrently check public transport routes, rideshare availability and costs, and walking directions using different tool integrations. Gives the survivor multiple immediate options tailored to their situation.
And for content generation with multiple components.
Yeah.
Like that safety plan example.
Yes. Generating a tailored safety plan. Concurrently draft a section on emergency contacts, a section on immediate safety steps, like securing documents, and a section on legal protections and reporting mechanisms. Significantly speeds up assembling a comprehensive, critical plan.
What about checking things? Validation.
Yeah. Validation and verification is another strong use case. When verifying incoming support requests, you could concurrently check for valid contact info, identify potential spam hoax attempts using pattern recognition or external databases, and flag keywords indicating extreme urgency or danger. This multi-pronged check enhances system reliability and safety.
Okay. And multimodal processing, like that voice message example.
Exactly. If a survivor sends a voice message, your system could concurrently transcribe the audio to text, analyze the spoken words for sentiment entities, and identify background sounds for distress indicators or threats. This integrated simultaneous processing significantly speeds up initial triage for a faster, more informed response.
Finally, A/B testing or multiple options generation. You could generate multiple empathetic response options to a sensitive query in parallel, each slightly different. Then, use another LLM or predefined rubrics to select the best one based on tone, helpfulness, safety protocols. Ensures the best possible communication in sensitive moments, refining the AI's compassionate support. This code shows you how to essentially tell your AI, go fetch all these different pieces of info or generate these different components at the exact same time. For your crisis bots, this means no more waiting for one database lookup before starting another, or one part of a safety plan before the next. It's about delivering help faster, making your AI far more responsive when time is critical. This is how LangChain handles it with LCEL.
What's truly fascinating here is how LangChain's runnable parallel allows for an incredibly efficient information gathering and content generation phase. Imagine your crisis bot needs to, all from an initial report. Generate a concise summary, compile a list of immediate action items, and identify key local resources. This parallel approach allows those three crucial pieces of information to be processed concurrently, significantly reducing the time to deliver actionable support to someone in need. It's a direct improvement in the speed and quality of intervention.
Let's walk through it. After installing LangChain and LangChain OpenAI, set up your LM, maybe chat OpenAI, model GPT-4 Mini, temperature 0.7. Then define 3 independent runnable chains for specific tasks. Summarize chain, summarize a topic, questions chain, generate 3 questions, terms chain, identify 5-10 key terms. Each is a chat prompt template piped to the Elm, then Stroutput parser. Critically, they all operate independently on the same topic input. No chain relies on another's output to start.
That independence is key for parallelization.
Exactly. The parallel block is where the concurrency magic happens. Map chain, runnable parallel, summary, summarize chain, questions chain, key terms, terms chain, topic. Runnable pass-through. This runnable parallel takes all 3 chains and runs them simultaneously. It also passes the original topic through using runnable pass-through for context in the final synthesis step. Then, a synthesis prompt takes summary, questions, key terms, and topic as inputs, designed to weave them together. The full parallel chain pipes map chain into synthesis prompt, then to the Elm and Stroutput parser. When you execute this with asyncio.run, run parallel example test topic, with a topic like the history of space exploration, it performs those 3 distinct LLM calls concurrently, and then synthesizes the results into one comprehensive output.
And it's worth noting, as you mentioned, Python's asyncio provides concurrency, not true parallelism due to the GIL. But for I/O-bound tasks like waiting for multiple LLM API responses, it still gives significant performance gains by managing those waiting times efficiently. Makes the bot feel much faster.
Right, so how does Google ADK handle this?
This brings us to Google ADK, which provides primitives like parallel agent and sequential agent for building concurrent execution into multi-agent systems. This ADK example powerfully showcases defining multiple subagents for specific, independent research tasks, and then using a parallel agent to run them all at once. For crisis organizations, think specialized bots. One for legal info, another for mental health resources, another for safety planning. They gather info in parallel, speeding up research. Then, a distinct synthesis agent pulls it all together into a comprehensive attributed report for the survivor or caseworker. This structured approach, especially with strict grounding and provided inputs for synthesis, greatly enhances reliability and trust.
Okay, walk us through the ADK code structure.
In the ADK code, you first define several Elm agent instances as specialized researchers, like Research Agent 1, Renewable Energy, Research Agent 2, Electric Vehicles, etc. Each Elm agent has a name, uses a Gemini model, accesses a Google search tool, and has an instruction to summarize findings concisely. Critically, they use output key, like renewable energy result, to store results in the session state, making them accessible later.
So each researcher puts its findings somewhere specific.
Exactly. Then you create the parallel agent, named Parallel Web Research Agent, giving it a list of these researcher subagents. This parallel agent orchestrates their concurrent execution, running them all at the same time. It only finishes once all its subagents have completed their research and stored results in the session state. Following this, you define a merger agent, another Elm agent. Its instruction is specifically to take results from renewable energy result, F-technology result, etc., directly from the session state and synthesize them into a structured report. A key instruction here is to emphasize exclusively using the provided input summaries, no external knowledge, and provide strict output formatting with headings and attributions. Ensures grounded, transparent synthesis.
Got it. Parallel research, then grounded merging. And how is it all tied together?
Finally, a sequential agent named Research and Synthesis Pipeline acts as the main orchestrator, defining the overall workflow. It explicitly specifies parallel research agent runs first, populating the state, then merge agent runs, producing the final output. The sequential pipeline agent is set as the root agent. This demonstrates a robust multi-agent system. Complex tasks broken into parallel research, findings combined sequentially, all within a structured, manageable framework. Okay, parallelization at a glance. What? Purely sequential execution is incredibly inefficient for tasks with independent subtasks, especially those involving waiting for external I/O, APIs, databases. Why? Enables simultaneous concurrent execution of independent tasks, tool uses, LLM calls. Frameworks provide constructs to manage concurrency, drastically reducing total execution time and improving responsiveness. Rule of thumb: use parallelization whenever a workflow has multiple operations that don't depend on each other's immediate output and can run simultaneously. Ideal for fetching data from several APIs, processing distinct data chunks, generating multiple content pieces for later synthesis.
And as you can see in the visual summary, a single prompt leads to multiple agents executing in parallel, each producing its output, which then funnels back to the user, providing a consolidated, rapidly generated response.
The key takeaways for parallelization are clear. Executes independent tasks concurrently for maximum efficiency, making agentic systems far more responsive. Especially useful when tasks involve waiting for external resources, API calls to shelters, legal aid. We should acknowledge adopting concurrent parallel architecture adds some complexity and cost, design, debug, logging, but performance benefits often outweigh this. However, frameworks like LangChain and Google ADK offer robust built-in support, abstracting away much complexity. LCL's runnable parallel is key in LangChain. Google ADK uses LLM-driven delegation. Ultimately, it significantly reduces overall latency, making your agentic systems more responsive, more capable of delivering timely support for complex, urgent tasks. Hashtag tag conclusion.
Wow, what an incredible deep dive into the world of agentic AI design. We've covered the 3 foundational agentic design patterns: prompt chaining, empowering sequential reasoning and precision; routing, enabling dynamic decision-making and adaptive pathways; and parallelization, boosting efficiency and responsiveness through concurrent execution.
And it's crucial to remember these patterns aren't mutually exclusive. They are incredibly powerful when combined synergistically. They form the sophisticated architectural backbone for truly robust, intelligent, scalable AI agents. Think of them as the fundamental grammar of building truly advanced AI.
You started this deep dive as a proficient prompt engineer, and now, hopefully, you have a mental roadmap, a blueprint, for building truly intelligent, adaptive, efficient AI systems. You can clearly see how applying prompt chaining to meticulously clarify urgent needs from a survivor's initial message, routing to intelligently direct them to specific, tailored help, be it emergency contacts, legal aid, or emotional support, and parallelization to gather crucial resources rapidly and simultaneously. How all this can absolutely revolutionize and dramatically enhance the support offered by domestic violence crisis response organizations. These aren't just technical patterns, they are tools for profound impact.
Mastering these patterns moves you beyond simple chatbots that just react to single inputs. It's about creating AI solutions that can genuinely make a profound, potentially life-saving difference in complex, sensitive, time-critical situations. It's about empowering your AI to be not just a responder, but a proactive, intelligent, empathetic assistant that can truly understand, coordinate, and act.
As you continue to build and innovate for such critical applications, maybe consider this. In high-stakes situations like crisis response, where every second and every nuance matters, how might the seamless integration of these agentic patterns, coupled with, judicious human oversight and real-time feedback, redefine not just what's possible for AI, but what empathetic and life-saving truly look like in a digital support system designed for profound human connection? It's a powerful thought to take with you, pushing the boundaries of what AI can achieve in the service of humanity.